without having to use an evolutionary algorithm in the real world. It doesn't have to perform thousands or tens of thousands of trials before it finds this gate. Okay, so moving on to slide 12 now. If you can play video 12 for me. Now we reach in and we introduce a perturbation or an unexpected change, which in this case is to physically separate part of the robot's leg. Now our robot does not have a camera, so it cannot see the fact that its leg is missing. It doesn't have any pain receptors, so there's no way for our robot to directly detect what's gone wrong. The only thing our robot can sense is that something has changed. So I haven't mentioned yet what the sensors are. Our robot basically has two sensors, two vestibular sensors, one which records how much the main body tilts left and right, and how much the main body tilts forward and back. So when it moves its various body parts, it can sense the tilt or change in tilt of its main body. So during the course of moving, our robot has suddenly sensed that something has changed but doesn't know what's gone wrong. So what it does is to go back to the first evolutionary algorithm. So if you can now play video 13 for me. You'll notice it starts with the self model like before, but now it starts to change that model slightly, and you'll notice that the leg on the right, first it thinks that leg has shrunk, but that doesn't make physical sense. So it eventually discovers that it's now made up of only 3.5 rather than 4 legs. So now, if you can play video 14 for me, our robot starts or reinitializes the second evolutionary algorithm and discovers that its original way of walking is no longer appropriate for its new body image or its new self-model. So that second evolutionary algorithm discovers this new gait that you see here. So now automatically the evolutionary algorithm has discovered that its previous mode of operations is no longer appropriate and that it has to regenerate or re-evolve a new behavior. If alternatively that damage had been very slight, or if there had only been a slight change in its environment, that second evolutionary algorithm might have realized that the original gait is just fine, but it just needs to adapt that gait slightly. So using this approach, our robot can switch between robustness and resiliency. So it can decide, in a sense, automatically whether to adapt its existing behavior to account for the change, or discard that behavior and try a completely new behavior. So now that it's found this new gait, if you'll play video 15 for me. You'll notice that now it is able to move again. Obviously, this gait is not as efficient or not as graceful as the previous gait, but it's still able to recover some functionality and continue with its task, which in this case is forward locomotion, despite the fact that it's incurred this injury. So just to give you some background on this project, after conducting my PhD with Rolf in Zurich, I began a postdoctoral appointment 3 years ago at Cornell University here in the United States with Hod Lipson, another relatively famous evolutionary roboticist who you might hear over the course of these lectures, his name mentioned. At that time, we were approached by NASA, the United States Space Agency, who's interested in trying to use some of these evolutionary robotics techniques in their future robot probe missions to the outer solar system. So as you can imagine, one of the main fears that NASA has is that they send a probe to a moon in the outer solar system and something happens to that robot on site that no mission controller back on Earth can fix. So that's the reason why we focused on physical damage. This is something that's a real worry for NASA in their future robot probes. And NASA's idea is to try and use ideas from traditional robotics, or to use the human engineers to try and figure out what's gone wrong before resorting to evolutionary algorithms. So this was a project that was developed for them as a method of last resort. So let's imagine they send a future probe to the outer solar system. Something goes seriously wrong, like what you just saw. But for some reason, the telemetry or the sensors that the robot has is not sufficient to directly diagnose what's gone wrong. So let's assume that our robot cannot communicate back to mission control the fact that I've lost my right leg, what should I do? That's exactly the case that our robot has. As I mentioned, it cannot sense directly what's gone wrong. Rather,